All right, chapter 9 and chapter 10 are all about convergence and divergence. So we're going to talk about how that applies to three different things. First, we're going to talk about how it applies to sequences. Then we're going to talk about how that applies to integrals that diverge or converge. All of our integrals so far have converged. We haven't done any divergent integrals. And then we will talk about series and sums, and that's the real kicker. Okay, that's going to take us all of chapter 10 and almost a whole month to cover. Okay, that's the big one. So we're going to do sequences and integrals in chapter 9. Chapter 9 will be a short chapter, so short that we'll be having a test next week. Okay, because we already did part of chapter 9, which was L'Hopital's rule. That's in this book. They put it in chapter 9. So we only have to do 9.1. Look at 9.1, 9.3, 9.4, 8, 4b done. That's the end of chapter 9. Really short chapter. I thought about combining chapter 9 and chapter 11, but then and just doing it as one big unit and taking one test. Then we'd only have two tests. The whole semester, and I thought, let's just do a short one, take a test, everybody get a nice good grade on it. Okay. And then it's better to have more tests than fewer, because the fewer tests you have, then the more, the weight they carry. So yeah, we'll only be in chapter 9 for like a week and a half, and then we'll sit in chapter 10 for a good amount of time, and then chapter 11 we'll whip through at the very end as well. Okay? All right, so sequences. So the title of today, I left it off, Convergence versus Divergence in terms of a sequence. All right, there are, besides converging and diverging, there are two kinds of sequences. So sequence types, this will be review for you, should be review. Okay, number 1, something called arithmetic. And then number 2, something called geometric. Okay, the title of the sequence is determined by the type of pattern that is being formed by the sequence. Okay, arithmetic is the pattern of addition. And geometric is a pattern of multiplication. So what do you do with a pattern of subtraction? Why? Exactly, okay? Subtraction is also arithmetic because it's just adding a negative number. What do you do with division? Okay, because division is the same as multiplying by the reciprocal, right? So it doesn't matter. It's not like you need a special one for subtraction and division. They are both, they're both either subtraction is addition and division is multiplication. So those are the types of sequences. Okay. After you define the type of sequence, there are sequence definitions. There are 2 of those also. They are either defined explicitly and an explicit sequence uses the variable n. And n is replaced by the counting numbers, and n counts from starting with 1, 2, 3, 4, etc. So you just generate the sequence starting with, I'm going to plug in 1, I'm going to plug in 2, I'm going to plug in 3, I'm going to plug in 4. That's called an explicit. So let's do an example of that. A sub n is defined as -1 to the n divided by n squared plus 2. Okay, this is called an explicit sequence because based on the value of n and is generated, we put brackets to show that we're starting the sequence, and we start plugging in numbers. Okay, so you plug in the number 1. When you plug in the number 1, you get -1 on the top and you get 3 on the bottom. When you plug in the number 2, what do you get on the top? +1, and you get 6 on the bottom. You plug in the number 3, you're back to -1 on the top with 11 on the bottom. And then 1, 18, etc. Okay, so this is an explicit sequence. It's infinite. And we'll be talking about, does that sequence converge toward a particular number, or does it diverge? The advantage of an explicit sequence is you can jump really far down the line of the sequence to a particular number with a great amount of ease. Okay, in other words, I can jump to the 100th term simply by plugging in the number 100. What will the numerator be for the number 100? It'll be 1 because it's a positive it's a even number. Okay, and the denominator for the number 100 would be 100,002. All right, so it's, oh, I have my comma in the wrong place. 10, here we go, 10,002, right, too many zeros. So an explicit sequence, allows you to jump around in the sequence and get to numbers that you want to get to pretty easily. Okay, the other kind, do you remember what it's called? We've got explicit sequences. Recursive. Yes, recursive. Okay, so we can also define them recursively. That does not use the numbers 1, 2, 3, 4, and on up. It uses the value of the previous term plugged in to generate the next term. And so the previous term generates the next term. Okay, that's indicated with a subscript of a sub n minus 1. So the previous term, let me see if I move this over a little bit. Okay, the previous term is a sub n minus 1. That will generate the next term, which would be a sub n. And then that term would generate the next term, which would be, which generates the next term. And the next term would be a sub n plus 1, which generates, etc., and it just keeps going on and on infinitely. Okay, that was called a recursive sequence. So an example of that, if you're not starting with the number 1, what do you have to know? You got to know what you're starting with, right? It's not going to be the number 1. The other one always starts with the number 1 being plugged in. This one, you have to know what the term is that you're starting with. And so you are given, say, the first term to be 3. And then you're told to generate the next term, you'll take the previous term and add 5. And so then that would create the sequence that starts with the number 3 and then goes to 8, which generates the next term of 13, which generates the next term of 18, which generates the next term of 23, etc. And that's an infinite sequence as well. Okay. So we've talked about sequence types, arithmetic or geometric. We've talked about sequence definitions, explicit versus recursive. And now we need to talk about sequence graphs. Again, all of this should theoretically be review, but you haven't done it since Ham probably. Maybe even Algebra 2. All right. To graph these two different ones, explicit has to be in parametric mode. Which is dot mode. And number 2, recursive, needs to be in sequence mode. All right, so let's practice that a minute. Okay, so grab your calculators out. We keep going. All right, so let's talk about convergence and divergence, okay? Let's define the two. All right, if the limit of the sequence, in other words, like the last term, as n approaches infinity, so it means if you've extended this sequence all the way out, if that approaches an actual number, like an asymptote, this would be really great for a horizontal asymptote, then the sequence converges. That's an n. All right, if the limit of the sequence, it's the final term, it's the terms all the way out as far as you can go. If they actually, so again, think horizontal asymptote. Think AKA, also known as horizontal asymptote. And then if the limit as n approaches infinity, sorry, my n's are looking like h's, aren't they, Catherine? Okay, let me see if I can fix it. Okay. All right. Of the sequence does not exist, then the sequence diverges. Is what? No. Because in a limit you could have like, I mean, in a sequence, you could have one term be really big positive and one big negative, and it's oscillating back and forth. So one's going to infinity and one's going to a negative infinity. That means the limit does not exist because of oscillation. Okay. Then you would say that it, yeah, so then that still considers, that converges to infinity. It's approaching infinity. I don't think that you'll have that. Okay. All right. So determine the convergence of the following. All right, so let's do the limit as n approaches infinity of the following sequence. You can always tell you're working with a sequence because of the brackets. Okay, so you're just going to approach this as we did with any limit. Okay, divide through by the highest power. So when we divide through by the highest power, we're going to get 2 minus 1 over n. And when you plug infinity into that, what do you get? 2. So this sequence converges because it actually had a limit of had a horizontal asymptote of 2. Okay. All right, next one. All right, the limit as n approaches infinity of the sequence -1 to the n. We've seen that before, just in a previous problem. What did the -1 to the n do to the sequence as we were working? Yeah, it was positive, then negative, positive, negative, positive, negative. All right, so we already know that this thing is going to be positive, and then negative, positive, and negative. And then times n minus 1 over n. All right, so recognize this as oscillating. We're going to call that alternating. Okay, alternating sign. All right, so we have an alternating sign, and then what happens to the rest of it? Okay, so the limit as n approaches infinity. If we divide that by the highest power of n, we end up with 1 minus 1 over n. Okay, so what will happen to this portion of it? That goes to 1. But what happens to the other part of it? It's alternating, right? So the sequence of this is going to be bouncing back and forth between 1 and -1, 1 and -1, 1, -1. So we're looking at values that do this. Okay, 1, -1, 1, -1 for forever. Okay, that does not approach a single value, and so this is diverges. Alternating sequences are going to always diverge unless that other part of the limit would approach what? What's the only number that would make it converge? 0, because then you would be at least plus or minus 0, and you would be converging on 0. But any other number in alternating is going to be a divergent. Okay, last thing. All right, make your own formula. I always kind of liked these. Okay, so if I give you -2, +4, -8, +16, -32, etc. Okay, could you make your own formula for that? All right, well, right away you notice it alternates. So you want -1 to the n. Now make sure that if you plug 1 in that you get the right sign. I need to start with a negative number. So if I plug 1 in, I'm guaranteed a negative number to start with, so that's good. And then what's the other thing doing? Okay, so powers of 2 or multiplying by powers of 2 or multiplying by 2. So you say 2 to the n power. Oh, you could do that as well. But sometimes it's helpful to separate the alternating piece, like later on when we get to doing integrals and stuff, to have that alternating piece be separate. So you might just want to train yourself to have that be pulled out. Okay, all right.